isn't it? So for distortionless line, Lg equal to Rc, okay, and we analyzed the formula and we concluded that we need to increase the inductance of the line, okay. So we are increasing the inductance artificially on the line. That is called loading of a line. The process is called loading, and that line is called loaded line. Now we will see Campbell's equation. So if we want to analyze the performance of the loaded line, that can easily be carried out using this equation, Campbell's equation. So an analysis for the performance of a line loaded at uniform intervals can be obtained by considering a symmetrical section of a line from the center of the center of one loading coil to the center of the other next coil. The section of line may be replaced with an equivalent T section having symmetrical series. See, we already have seen the equivalent T section. Okay, T section equivalent of a transmission line we already solved, and I told you to solve for pi equivalent. How many of you have solved that problem? Derivation. Have you completed that part? During class, we have seen how to arrive at T equivalent of a transmission line. And I told you to work out for pi equivalent. Did you complete that? No one is completed. So in one class we derived the T equivalent. Do you remember that?
Yes, ma'am.
Yes, ma'am.
Okay. So we derived the T equivalent of a transmission line. Okay. And if you have not solved for pi equivalent, you try that. Okay. See, the transmission line can be equivalently drawn using RLCG components. The same can be drawn using T network or pi network. Okay, and we saw the relation between T network and the secondary constants. Okay, now we are taking the same T network and we are going to analyze the loaded line using the T section. See, generally the transmission line will be drawn equivalently using T section this way. Since we are including the inductance on the line, so that inductance coil, okay, that inductance for symmetrically analyzing the line, we are taking that as ZC by 2 on both sides of the T section. Okay, so this is the equivalent T section for part of a line between two lumped loading coils. We are including the inductance, okay. That inductance coil, that coil inductance is ZC. To analyze it using symmetric T section on either side, we are taking ZC by 2 as the inductance. Then the series sum of T section including loading coil, okay, including loading coil. So yeah, already it was Z1 by 2. Since we included the inductance, okay, we have included additionally some inductance ZC by 2 on both sides. So the series sum of T section will be Z1 dash by 2 equal to ZC by 2 plus Z1 by 2. And we already know that Z1 by 2 is related to the secondary constants of a transmission line, this form, Z0 tan H nu L by 2. Okay, so for this Z1 by 2, we can write Z0 tan H nu L by 2. and L is the distance between two loading coils. Then shunt arm Z2. Shunt arm we have impedance Z2, and we know the relation, that is Z2 equal to Z0 by sin H nu L. Now we now need to find the relation for the loaded line. Okay, so here actually this cos H nu L equal to 1 plus Z1 by 2 Z2. This is the relation, general relation relating the Z1 Z2 propagation constant. Okay, generally cos H nu L equal to 1 plus Z1 by 2 Z2. Now we are denoting the propagation constant for the loaded line as nu dash. Okay, propagation constant of the loaded line as nu dash, and for the loaded line only the series impedance is changing, so that Z1 we denote as Z1 dash. We already have written the expression for Z1, Z2 for the loaded line. Substituting here, then after simplification, we get this relation. Here cos H nu dash L equal to ZC by 2 Z0 sin H nu L plus cos H nu L. See, this is the we have seen the relation for series of impedance. Series of impedance of loaded line is this one, and for the loaded line there is no change in the shunt arm, so Z2 remains same, and we are taking the relation cos H nu L equal to 1 plus Z1 by 2 Z2. That is for general expression, and for the loaded line we are denoting nu dash. Just a second. Okay. So for the loaded line, am I audible, students? Audible,
Yes,
students?
ma'am.
Okay. So for the loaded line, we are denoting the newer propagation constant as nu dash, and the impedance is only the series impedance changes. So that is Z1 dash, and the okay. Z2 there is no change. We are keeping as it is. So cos H nu L dash equal to cos H nu dash L equal to 1 plus Z1 dash divided by 2 Z2. So substitute the expression for Z1 dash and Z2. Okay, we are getting this. And this tan H nu L by 2 can be written as cos H nu L minus 1 divided by sin H nu L. So we are going to substitute this. Then after that, you simplify it. So after simplification, we are arriving at this relation. That is cos H nu dash L equal to ZC by 2 Z0 sin H nu L plus cos H nu L. What is nu? Nu is the propagation constant of unloaded line. ZC is the coil, that loading coil impedance. Z0 is the characteristic impedance of the line. Nu dash is the propagation constant of the loaded line. So using this, we are able to get the relation between propagation constant of the loaded line with propagation constant of unloaded line, the coil impedance Z0. So if from this relation, we will be able to identify what will be the propagation constant of the loaded line. Okay, so the propagation constant of a loaded line can be found using propagation constant of the unloaded line ZC Z0. Okay, if we know nu ZC Z0, then nu dash can be found. So that is the use of Campbell's equation. Whether this relation clear to you?
Yes, ma'am.
Okay. Next, we are going to see about reflection on the line. When the load impedance is not equal to the characteristic impedance of a transmission line, reflection takes place. Okay. When the load impedance is not equal to the characteristic impedance of transmission line, reflection takes place. So we already have derived the transmission line equations for at any point on the transmission line, how voltage and current can be found. Okay, for that we found the general solution of a transmission line, that only we are taking. But here, instead of writing a voltage as E, here it is written as V, both same only. Both are same only. Whether we write as E or V, both are same. Okay, so we already have derived these equations, but we have denoted the quantity as E, ES, ER, that's all. But both mean the same. So we are taking this voltage and the current equation, and we already seen that those equations can be written in many different ways. Here, and it can be rearranged and arrived at this form also. And while deriving these equations, I told that this is having some significance, which we will be seeing it that later. Okay, so this component we derived and simplified to this form. In this, we have this ZR minus Z0 divided by ZR plus Z0. One term is present, About that only we are going to see now. See here, e power nu s is one term. The other term is ZR minus Z0 divided by ZR plus Z0 e power minus nu s. Okay, this equation is having two types of waves. One is transmitted wave, the other is the reflected wave. Okay, here e power nu s. Okay, what is s? S is the distance from the receiving end to the point we consider. Okay, so as the distance increases, e power nu s value will increase, which means the total this wave amplitude is increasing. Okay, so transmission line, load, load is connected here, and S is the distance from the transmission line to the point we consider. Okay, in case we are calculating V and I at this place. Okay, this is the distance from the receiving end to the load. Okay, so if this S is increasing, means we are going towards the source. We are going towards the source. Hence, the transmitted signal will be having maximum amplitude here. Okay, and if the line is lossy, when it progresses towards the line, it may decrease its amplitude. Okay. Don't consider how I have drawn this. Consider this as only a sine wave. Okay. Once if the transmission line is lossy, it will be going on the transmission line with reduced amplitude. Okay. So as S increases, we are going towards the source. So this quantity denotes that component. So this is denoting the transmitted signal. This is denoting the transmitted signal. Okay. So what about this? The second part present in this equation, ZR minus Z0 divided by ZR plus Z0 e power minus nu s. Then what type of wave is it? As S decreases, then the quantity value increases. Then what wave it is, whether it is a transmitted wave or a reflected wave?
As S increases, its value, e power minus us value, this value amplitude is decreasing. Okay, so once we go away from the load, it is decreasing. Okay, so this is the reflected wave. This denotes the reflected wave. So when reflected wave will be zero, can you tell? When reflected wave will be zero?
LG minus RC is equal to 0, ma'am.
Infinity.
Please repeat.
When LG is equal to RC.
That is for distortionless line. Okay.
Ma'am, then ZR is equal to 0. So ZR is equal to Z naught.
Yes. When ZR equal to Z naught, you see ZR equal to Z naught, that time this term, okay, this will become 0, isn't it? When ZR equal to Z naught, this term becomes, this entire term becomes 0, then the reflected wave will not be there. Reflected wave will not be there. But when ZR not equal to Z naught, when ZR not equal to Z naught, there will be reflection. Okay, so in the general solution of a transmission line itself, there are two components present. One is the transmitted signal, the other one is the reflected signal. So whenever the terminated impedance, that is the load impedance or the receiving end impedance is not equal to characteristic impedance of the line, there will be some reflections. Okay, if the reflection, if the mismatch between ZR and Z0 is more, reflection will be more. If the mismatch is less, then the reflection will be less. So that is what given in these slides. Okay, so relating to that, we define few quantities. Okay, so how much reflection is present on the line can be obtained from few parameters. So one parameter is reflection coefficient. It is defined as the ratio of the reflected voltage to the incident voltage at the receiving end of a line. It is defined as the ratio of the reflected voltage at load to incident voltage at load. So VR by Vs. So if we write VR by Vs, then we get reflection coefficient as ZR minus Z0 divided by ZR plus Z0. So this is the expression for reflection coefficient. The reflection coefficient can also be denoted using this function gamma. Okay. Reflection coefficient gamma or K equal to ZR minus Z0 divided by ZR plus Z0. Just a second. So the reflection coefficient is the ratio between reflected voltage at load to the incident voltage at load. So if we find that ratio, we are getting ZR minus Z0 divided by ZR plus Z0. So this is called reflection coefficient. It is denoted using symbol K or gamma. And using the current also, it can be defined, that is reflected current at load divided by incident current at load. That time it will be having negative sign. This reflection can be quantified using many factors. The other factors are reflection factor, reflection loss. So the power delivered to the load is less than that with impedance matching. So if impedance mismatch is present, then the power delivered to the load will be lesser, considering the case of impedance matched condition. And the reflection results in power loss, that is called as reflection loss. Okay, the reflection factor is defined this way. The ratio of the current flow actually flowing in the load to that which might flow under matched condition is known as reflection factor. The ratio of the current actually flowing in the load to that which might flow under matched condition is called as reflection factor. Okay, and this is the formula for reflection factor. That is here Z1, Z2 are given. Z2 is the load impedance, Z1 is the source impedance. Okay, if Z1, Z2, okay, Z1 is the source impedance, Z2 is the load impedance, then the reflection factor small k equal to magnitude of 2 square root of Z1, Z2 divided by Z1 plus Z2. And these are somewhat lengthy derivations. Okay, so we skip those part. You remember only the formulas, but if you have interest, you go through book, and if any doubt you can ask me. Then the reflection loss. Okay, reflection loss is defined as ln of 1 by k. Reflection loss is the reciprocal of reflection factor in meters or dB. So if we take inverse of reflection factor, okay, reflection factor, and for that if we take a natural logarithm, we get the answer in meters. Okay, for that reflection factor, if we take 20 log, we get dB. The reflection loss can be mentioned using meters or dBs. So for the reflection factor, okay, in 1 upon k, if we take natural log, we get the reflection loss in meters, and if we take 20 log, we get reflection loss in dBs. And voltage and current on dissipationless line. Dissipationless line means attenuation is 0. Okay, if there is no attenuation, that line is called dissipationless line. So alpha is 0. That time the voltage and current on the line will be like this. This is the voltage, and current will be constant on the line. And one more condition is that load is matched. Okay, when the load is matched, the receiving end impedance matches with the characteristic impedance of the transmission line. So and also here we consider the quantity is only real, so RR equal to R naught. In case if the load is short circuited, okay, if the load is short circuited or open circuited, that time that impedance, the receiving end impedance will be, if it is open circuited, receiving end impedance is infinity, and short circuited receiving end impedance 0. That time reflection will be maximum. Reflection will be maximum. So for that line, the voltage waves like this. This is for open circuit condition. So the voltage is maximum at the receiving end, current is minimum at the receiving end. This is the current waveform, and this is the voltage waveform. This is for open circuit. And for short circuit, the voltage is 0 at the receiving end, current is maximum at the receiving end. So this is the current waveform and this one is the voltage waveform. So if it is a matched line, then the voltage and the current will be like this. So in this class, we have seen Campbell's equation. It relates the propagation constant of unloaded line with the loaded line. Okay, so if the unloaded line propagation constant and the loading coil impedance, characteristic impedance of the line are known, then the propagation constant of the loaded line can be found that using this relation, Campbell's equation. Then we have seen about reflection. Reflection will be present on a line if the impedance mismatch is present. Okay, the impedance mismatch we say between the receiving end impedance and the characteristic impedance of the transmission line. If both are not equal, then reflection will be present on the line. So that is quantified using many parameters. One quantity we mostly use is that the reflection coefficient. The reflection coefficient gamma or k equal to ZR minus Z0 divided by ZR plus Z0. ZR is the receiving end impedance. It is also called as terminating impedance, or it is also called as load impedance. Z0 is the characteristic impedance. And this can be found using the current also, reflected and incident current also. That time we define it using negative signs, because the current, as far as current is considered, the direction of the current changes. So it is denoted as minus K. Then the reflection can also be defined using other parameters. The one such parameter is reflection factor. The ratio of the current actually flowing in the load to that which might flow under matched condition is known as reflection factor. If we derive the equation, we get K equal to magnitude of 2 square root of Z1 Z2 divided by Z1 plus Z2. And using this reflection factor, we can define reflection loss. Natural log of 1 by k will give reflection loss in meters. 20 log 1 upon k will give us reflection loss in dB. And how the voltage and the current will be on the matched line, in the open circuited line, in the short circuited line also we have seen. Any doubt? Okay. Take down this problem. Now we will solve few problems. All of you take down this. A transmission line has a characteristic impedance of 50 ohm and a resistance of 0.1 ohm per meter. If the line is distortionless, then determine attenuation constant. Determine attenuation constant, alpha. Can you work out this problem? How will you work out this problem?
Ma'am, the answer is 0.02, ma'am.
Very good.
0.02.
Who told them?
Roll number 43, ma'am.
Name?
Sanchit.
Sanjay. Good. Other people also. So what is the formula for attenuation? Distortion line.
Alpha is equal to 1 over RG. Where
Good. So in your problem, R is given. What will you do for G?
ma'am, there are R by not.
Good. See, we know S is equal to R by G. From that, and also we know the characteristic impedance is not equal to root of A by C, which can be equal to root of R by G. So G can be written as root R divided by Z naught. This is the procedure. 0.0002 meter per meter. Point 002 meter per meter. Next, take down this problem. In a two-way transmission line in air, the adjacent maxima are at 12.5 centimeter and 27.5 centimeter. Determine operating frequency. Okay, so about the maxima minima we will discuss in next class, but the distance between two adjacent minima or maxima is lambda by 2. The distance between two any adjacent minima or maxima is lambda by 2. So with that you find out the answer. See, the maxima locations are given 12.5, 27.5. Then the distance between adjacent minima is the difference between these two. That you equate to lambda by 2 and find out lambda, then find out frequency.
Ma'am, 10 to the power 9 hertz.
Okay. 10 to the power 9, how can we call?
1 gigahertz.
Yes, 1 gigahertz. Right answer. So other people, if you have doubt, you can ask. Okay. Take down this problem. A transmission line has a characteristic impedance of 50 plus J 0.01 ohm is terminated in a load impedance of 73 minus J 42.5 ohm. Calculate the reflection coefficient, the standing wave ratio. See, we already have seen the formula for reflection coefficient and its relation with the standing wave ratio. We will see the relation in the next class. Okay. Standing wave ratio can be related to reflection coefficient this way. And you know reflection coefficient. See here a transmission line has a characteristic impedance of 50 plus J 0.01 ohm. So the line is having almost 50 ohm impedance and the load given here is 73 minus J 42.5 ohm. Okay. So actually this is the impedance of dipole antenna. So load we can understand the load here is an dipole antenna. You will be seeing about the dipole antenna and its impedance, radiation resistance, everything in the antennas subject. Now have you found the answer? What is reflection coefficient value in polar form? Roll number 6 is there.
Yes, ma'am.
What is the answer?
I'm doing it.
Roll number 12. Roll number 12 is absent. Roll number 4. What is the answer? Anybody obtained? Right. Instant right. And what is yes? Standing wave ratio. Good. Good. Right. But your answer is much deviating. You check again. Vamsi, you check your answer. Can we have one class tomorrow? Can we schedule one class tomorrow? Okay. Okay, thank you, students.
Thank you,
Thank you,
ma'am.
ma'am.